Okay, okay, okay. All right, here we go. YouTube. Boom. Go away. Calculator, go away. There you go. Okay. Informal definition of a limit. So this idea, this whole idea of having the slope of the secant line approach the slope of the tangent line, it's a big idea for understanding the idea behind limits. Now, again, without limits, we don't get calculus. Okay? So we have to introduce this concept of limits. They're very important, and they're a lot of fun. So what this means is the limit as x approaches a, the limit as x approaches a, or the inputs as the inputs approach a, the function values or the outputs for the y values approach some number that we call L. So for example number 7 that we just looked at in your book, what were the x values approaching? What were the x values approaching? Well, we're getting closer to 1. What were the outputs approaching? 0.5. Okay? So that would formally be written as the limit as x approaches 1 of the function, which was, we had x to the third over 6 minus 1/6 divided by x minus 1. That was our function. That was equal to 1/2. Okay? That's the idea. A lot of limits are very easy to calculate. In fact, if we look at this one, it says sketch a graph of the following functions and use the graph to visually determine the limit. F of x is equal to 1fx squared minus x plus 3. What shape does that make? Parabola, up or down? Up. In fact, it looks like that. You can graph on your calculator and find that out. And what would be a reasonable guess? We'll type in our calculator and we'll try to make a reasonable guess here. 0.5 x squared minus x plus 3. Zoom standard. Whoop-de-doo. Okay, as x approaches 3, or 2, excuse me, x approaches 2, I'm going to get really close to, what do the y values approach approximately? What do you think? Give me a guess. About 3? What would be an absurd guess? Ridiculous guess. -4, huh? I mean, it's obvious that function doesn't go down here, does it? Okay? So, what values is it getting really close to? Now, you could go to your table, and you can even type in values that are really close. Like, I'm approaching 2, so I can type in, say, 3. Oh, 4.5. I can type in 2.5. What can I type in after that? 2.1. 2.01. Oh, looks like it's going to what? Instead of approaching from this side, let's go from the other side. Let's plug in some other values. Yeah, type in 1. Type in 1.5. Type in 1.9. Type in 1.99. And you see that the values are approaching what? 3. So it sure seems like as x approaches 2, that the y values approach 3. In fact, the limit is 3. I show you an easy way to figure it out. Just plug it in. 2 squared 4 times 1/2, 2 minus 2 plus 3. It's 3. If we just type in 2 to our calculator, you can see you get 3. Now, why didn't that work last week? There was a hole. There was a number. We were dividing by something. You couldn't type in, say, 2 because you would get 0 in the denominator, right? Not the problem right here. Polynomials and rational functions, you could generally just plug in the number and you're good to go. It will give you the answer, okay? So, like, look at this one. Square root of x plus 4. What does that look like? Very good. Shift it to the left. 4 units. Goes like that. What is the x value approaching? 0. Let's plug it in. Square root of 0 plus 4 is 2. Sure enough, as you approach 0, the output does approach 2. It goes through 2. That was easy, wasn't it? So you can see that for a lot of functions, basically any polynomial radicals, you just make up a number that you want to approach, plug it in, and that will tell you the limit. It's because they're very nice behaving. They're defined for, in this case, the parabola is defined for all real numbers. You plug something in, you get something out. Here, as long as you approach something past -4, all x values greater than or equal to -4, you're going to get an output. Okay, so let's look at the special cases where that's not always so easy. Okay, look at this one. Why can't I just plug in 3 there? There's a hole. Yeah, it's undefined. I get 0 in the denominator. Okay, well, what does that graph look like? Do you know? I'll show you how to figure it out. What do you notice happens to the x minus 3? And so the graph really wants to look like this. It wants to look like x. What does the graph of x look like? Yep. But it does have a gap in it. And just to prove it to you, we'll go to our calculator. X squared minus 3x minus 3. Now you take a graph, right? Any gap there. But if you zoom as a decimal, number 4. Oh, look at that. See that? Look, as I move to the right, I can see the x values are going up. And as I get closer and closer and closer to 3, what are the y values getting really close to? Well, watch what happens right at 3. You see, you have a missing pixel right there. That's what this graph is right here. Okay? It wants to look like x. Wants to look like that graph of x because those would divide off. But it has a hole. Whoop. At x equals 3. What's the y value of that spot? Well, just plug it into x. If you plug 3 in for x, what do you get? 3. So you can see that that's your gap. Now, we have a gap there, but there could still be a limit. You don't have to have a function value in order for there to be a limit. Is that clear? We will come back to this all the time. This is what makes calculus possible. You don't have to have a filled-in circle for there to be a limit. Okay? Because it's approaching 3. It's approaching 3. Okay? As we get closer to 3 for the x values, the y values also get closer to 3. All right? Now let's look at a weird one. Let's look at D. Sine of 1 over x. Y equals, clear, sine, 1 divided by x. Should I be in radians or degrees? Radians. Mode, sitting in radians. Zoom standard 6. So let's look at the graph and see as x approaches 0. Can you tell what y is doing? Kind of tough to see, isn't it? I'm going to zoom in. I'm going to make a different window, actually. I'm going to go from -2 to +2 to -2 to +2. We're going to try that. Is it clear now? As x approaches 0, y approaches? I don't know. Better try again. Yeah. Let's try again. Let's zoom in here. I don't know what's going on. Haley Larson, stop the madness. What is this? She's mesmerized. She's speechless. She just doesn't know. Oh my goodness. Would you agree that all the outputs stay between -1 and +1? But that between there we have no idea what's going on? If you don't believe me, go to your table values and try plugging in stuff like, 0.1, 0.01, 0.001, 0.0001. And you try to tell me that those are all going towards a specific value, that they're going to hone in on some number. No way. And so when you have a graph that has this type of behavior, we can't tell where it's going. It does something like this. I think that's pretty good. Don't laugh at my graph. Thank you, Jack. It's nice to know where I have support in this classroom, namely the guys. So that's what happens. I got this erratic behavior, and so we actually say, anybody want to guess the limit? Mean Girls. Does not exist. All right, there you go. Thank you. Limit does not exist. DNE. We can't find a number that seems to hone in on, and therefore it's problematic. So earlier you guys thought, well, this is boring because all we got to do is just plug in a value and see what we get. Well, yeah, go ahead and try that here. Plug in 0 there and see how that works out for you. Well, you can't because you got 0 in the denominator. Well, we'll just look at the graph. Yeah, all right. There you go. All right. Do you know that you can use this function to generate all barcodes used across the United States? Barcode function. There you go. All right, so we flip it over. Let's get to the real stuff. Oh, you're out. Lunch. Come back. Ready to go. We got a lot of stuff to get through. Hi, Sarah. Oh, Sarah. How you doing, Sarah? You know my friend Mariah? I call her Miranda. I know it doesn't sound right, Mariah Miranda, but it's all good. It's all good. Thank you so much for your help. We sure appreciate it. Okay, let's do this. One-sided limits. So we haven't actually talked about this, but the fact is that there are one-sided limits. Yeah, there is. For example, for this example, we approached x from the left. So we typed in like 2, 2.5, 2.9, 2.99. We also approached it from the right. We went like 4, 3.5, 3.1, 3.01, so on and so forth. So when we talk about limits and we want to put forth eventually a formal definition, we talk about right-sided and left-sided limits. So left-handed and right-handed, excuse me. The limit as x approaches a from the left. So this negative sign there, if the negative comes to the right of the x value, it means that we're approaching it from the left. Okay? So if we have the limit as x approaches 5, then for this you would look at values like 3, 4, 4.5, 4.9, 4.99, so on and so forth like that, okay? And this, the limit, as x approaches a from the right. And we would look at numbers like, say, 7, 6, 5.5, 5.1, 5.01, so on and so forth. So sometimes people get confused about, oh, when do I type in 0.1, when do I type in 0.9? You got to think about it, okay? That's all I can say. You got to think about whether you're approaching from the left or approaching from the right. So everything we've talked about now with limits up until now has been a two-sided limit. We need you to kind of divorce your minds from that and now think about one-sided so we can then give a definition for two-sided limits. So let's look at this graph here. Let f of x be the graph to the right. Use the graph of f of x to evaluate the following limits. So I'm going to have x approach the value of -4. I want to know what the outputs approach. So as I approach from the left due to that negative, what do the outputs approach as I get x value very close to 4? -3. Very good. Is everybody convinced of that? Okay. Now I'm going to approach from the right. -2. However, I'm going to make a statement here. F of -4 is equal to what? What is f of -4? It is, if you plug in -4, you get an output of 3. So notice that the output is different than one of the actual limit values, correct? It's the same as one, but it's different from the other, isn't it? So that's okay. The function evaluated at that spot can be different than the limit or one of the one-sided limits. Yes. I just circled it so everybody could see I was approaching -4. Right there? Yes. So that means we do not evaluate it here. We evaluate it there. Exactly. Is that clear to everyone? All right. So for the next one, limit as x approaches -1 from the left. So I'm going to approach -1, and I'm going to approach from the left. What is the output? 4. I'm going to approach from the right. The output is 4. And if you actually did f of -1, what would you get? 4. So you can see that in this situation, the function value is the exact same as the one-sided limit values. We're going to do this one later. Let's go to 2. We'll approach 2 from the left. What do we get? -1. Approach 2 from the right. 5. And what is f of 2 if you actually plug it in? -1. Okay? So now we're going to answer a little bit more difficult questions, and that's the limit as x approaches 2. What is different about this problem compared to the 6 that we just did? It doesn't have the plus or the minus. Same as letter E. If it doesn't have a plus or a minus, that means it's a two-sided limit. In order for a limit to exist, in order for the limit as x approaches a of f of x to be L, that's true if and only if the limit as x approaches a from the right is the same as the limit as x approaches a from the left. So the two-sided limit exists if and only if the right hand is the same as the left hand. Got that? This is crucial. So let's go back at our examples. As x approaches -4, did the left hand exist? Does the right hand exist? The left hand exists and the right hand exists. But does the limit, the two-sided limit, exist? No. Why? Because they are different. Look at -1. Did the left hand exist? Did the right hand exist? Does the two-sided exist? because they are the same. 2 from the left exists, right exists. Does the limit exist for two-sided? No, because they're not the same. So look at 4. Let's do 4 right now. It says the limit as x approaches 4. What does the left side equal? 2. What does the right side equal? 2. So those are the same, so therefore the limit exists. It is 2. In this situation, as x approaches 2, from the negative exists, from the right it exists, but those are different. So therefore the two-sided limit does not exist. Does that make sense? You can always look at one-sided limits, but in order for the two-sided limit to exist, the right and the left must be the same. Now look at this example for this one right here. What if you did f of 4? If you tried to evaluate 4, what would you get? Undefined, right? I mean, the open circle is at 2. It wants to be 2, but if you actually plug in 4, do you get 2? You don't get anything. There's a hole there. Just like in the examples we showed you earlier, there's a gap. And so therefore, f of 4 is undefined. So if the function doesn't have a value there, can you still have a limit? Very good. If the right and the left side limits are not the same, can you have a two-sided limit? No. Okay. So that's an important diagram. You want to really kind of commit these cases to memory so you can understand them moving forward. All right. So today, all I want to do is I want you guys to practice. We'll get to example 3 and 4 and stuff tomorrow and continue to move along. Looks like I'll let you know tomorrow when the test is going to be. This first test usually goes very well. There's not a lot of real difficult content on it. I would say average scores are, up in the 90s. So I did print off your book pages for you, so that way you don't have to bring your book back and forth for these next few days. But your assignment is going to be section 2.2, page 79. We're doing numbers 4 through 7. It's basically going to be looking at the graphs like we just did and identifying right-handed and left-handed limits, but then also two-sided. Okay. I just want to make sure we understand in case a situation like this pops up here. Okay, so just look at this example with me really quick. Limit as f of x, limit of f of x as x approaches 3. Let's do from the negative. As you approach from the negative, the output is approximately about 2, right? Let's approach from the left. If your book shows this is that barcode thing that we showed for one of our examples. Remember the barcode function? So it's tough to tell, but it looks like, oh, well, it looks like it's going to 2 as well. When it shows this behavior, this is key for does not exist. Everybody understand that? Even though it looks like it's hard to show with your book. It looks like it connects right there. It just keeps on jumping up and down. Okay? And so does the limit exist for the two of them together? The two-sided limit? No, it does not exist. And if they asked you what is f of 3, if you plug in 3, do you get a value? No, it's undefined. So therefore, you only really have one that you can get a clear-cut answer for. Okay. So I didn't do a short example like that, so that should make sense to you now. All right, Hannah. Okay, we're done.